Another pair will classmates.
Sir,
Yes.
sir, did you call me, sir?
Okay, so this is what we have seen in the last class, CMOS inverter characteristics. Okay, we find that 5 reason of operations here. Okay, first reason is 0 less than Vn less than Vtn. That means this is the reason we talk about. Okay, so their NMOS and PMOS are something like this, and the current is 0 at this point. Okay, the second one is so this is the first region that we talk about. Okay, the second one is we talk about here is I got to report that one. That is the reason why I'm explaining again. The second reason is VTN to VDD by 2. At that one, NMOS and PMOS are the conditions are something like this. The current will flow since it is a both serial currents are equal, but non-zero current is flowing in this one. So in the reason number 3, so reason number 3, what is the reason number 3? So when Vn is equal to VDD by 2, okay, exactly at VDD by 2, what is happening? Both the transistors are at saturation, and here also the maximum. Here you observe that maximum current will flow within the inverter. Okay, non-zero current will be flowing here. It's the maximum current. The reason number 5 is actually reason number 5 is what happened if VDD by 2 to Vn. So therefore, this is the reason that I'm talking about. So this is the reason I'm talking about. VDD by 2 to VDD plus VTP. At that condition, both the transistors are, it's a reason of operations also we have mentioned there, and VTN is equal to VTP, it's not equal to 0. Okay. And lastly, and last one is the last reason of operation is, so this is what actually VDD maximum VDD plus VTP to VDD. So that means this is the reason that we are talking about. At that point, only NMOS is off, on, PMOS is off. But here you can say that inversion current is 0. So this is what we have seen in the last class. Okay. Now, we found that the switching threshold of a transistor also, our expectation is that the switching threshold should be at the middle point. Okay, if you want to get the middle point, we have to assume that beta n is equal to beta p. At that point, we can observe in this way. So normally, what will happen if two cases beta n is greater than beta p? That means PMOS, the beta n is more than that of the beta p. Okay, in that situation, what we can say, the switching threshold will move towards the ground side. Okay, switching threshold will move towards the ground side. So therefore, this is how now the switching threshold is something like this. So what about if beta n is less than beta p? So the switching threshold will move towards the VDD side. Here is a ground side, here is VDD side. Now, what is our observation is that we want to make this transition period. So this is what the transition period, as much low as possible, as much small is possible. Okay? It must be equal to the ideal characteristics. In order to do this one, what we have to do, we have to increase the Vn value from Vtn to some VDD point 2, and this was also something like this. So when it reaches to this, the Vn is for the logic 0 extended to VDD by 2, noise will be effectively reduced. Even if some noise is at the input side, that cannot be affect the inverter operation. Similarly, if the the logic 1 value is extended from VDD to VDD by 2, so that means this is where I want to talk about. So ఇక్కడ వరకు మనకి ఎక్స్టెండ్ అయింది అనుకోండి, సో దట్స్ వాట్ ఐ హావ్ ఆల్రెడీ రిటన్ హియర్. సో ఇక్కడ వరకు మనకి ఇక్కడ నుంచి ఇక్కడ వరకు రిటన్ అయింది అనుకోండి, దెన్ ఇట్ ఈస్ పాసిబుల్. సో సంథింగ్ లైక్ దిస్. So therefore, even if the noises existed in for the logic 1 value, it does not affect the inverter operation. Okay. So that thing is available here. Now we come to the another important point, alternative pull-up to pull-down ratios. This already we have seen in the previous class. The third point is enhancement pull-up. Last one is CMOS pull-up. CMOS. So these are the different pull-up networks that we have used there. And let us write its advantages and disadvantages. Already we have seen, but let us, for the completeness, we are going to talk about this one. And I want to paste it here. Okay, so we observe this one. This is the resistive pull-up. Okay, so in this resistive pull-up, what is the biggest problem with this resistive pull-up? So the area is high. Okay, so area requirement for resistor is high. Area is high, that we can say that. And the power consumed by the circuit is also, power is also very high at this point for the inverter. So normally when the sizes of the NMOS transistor and the resistor will be large spaces required for the resistor in an IC. Okay, so that's what we have to remember that. And one more thing is that you cannot find the VO output low value. We cannot find output low value comfortably. Okay, so we have to go for another approach is called enhancement, depletion pull-up network. Okay, so the theory, how it has derived the characteristics already, we have already seen. So I don't want to explain more and more about this because exclusively we have studied these points. Okay, the next one is a depletion mode type of transistor. As you can see that the most important observation is that there is a non-zero output for logic high value. So as we know that power is high because when Vn is equal to VDD, both the transistors are on. Therefore, the short circuit power consumption is observed there. And one more thing is that output low value is non-zero. It is a non-zero. It should be zero. Okay, so that is the biggest problem with this one. So related theory also we have studied there. Similarly, we have considered another one, enhancement pull-up network. It is actually very difficult to maintain the logic high value as well as the logic low value. It's very difficult to maintain the logic low value as well as logic high values. So this point also we have studied extensively. Okay, so here this is a problem. Okay, as well as this is also another problem. So therefore, output high value and output low value both are, it's not equal to zero. It's not equal to VDD. So therefore, it is not at all useful. One more thing is that we have to take the Vout normally from the external power supply. Okay, so VDD that we have to take it from usually from the other supply. So therefore, two supply voltages that are necessary for this one. Okay, so of course, it is also consumes the power. The power is also high. Why? Because when Vn is equal to VDD, both the transistors are on. Therefore, the power will be consumed for this one. The most effective one is nothing but CMOS inverter. So the CMOS inverter is a very prominent, very useful design when compared to these three. About the three considerations. Okay, so as you can see that there is a possibility of good VOH is exactly equal to VDD, VOL is exactly equal to 0. And only the problem is that the duration for both the transistors are on. This duration is actually we have to narrow down as much as possible by choosing the suitable sizes of the NMOS and PMOS and everything. Okay, but actually we have a good logic values for you by using this one. So the static power consumption, the power consumption is less, is decreases except at the middle point, and all the time the power consumption is whatever the under static conditions. So under static condition when Vn is equal to 0, you can see that the only one transistor is on. Therefore, there is no static power short circuit current. When Vn is equal to VDD also, only one transistor is on. Therefore, there is no possibility of the static current. So the short circuit current is not there from VDD to ground. Okay, it's not possible. So that's the reason why the power consumed by the CMOS devices are less compared to the other existing circuits. So these are the 4 alternative pull-ups that we have in our syllabus. Just please go through it once. And yeah, as we mentioned that the the biggest advantage of using the CMOS is, as I mentioned, that less power consumption, or less power dissipation. Okay, but we have to carefully design. But careful design is required. Careful design is required. Why? Because otherwise there is a problem of latch-up. Otherwise, latch-up problem is arises. Latch-up problem. So what is this latch-up? That's what we have to talk about. Careful design is required. What do you mean by a latch-up? Okay, so for that one, I'm going to use another slideshow. So please, I want to stop sharing this one. I want to share another one. Yeah, this is, so you can see here. So, so let us see the latch up related to the CMOS realizations. This is a very important concept. Whenever we talk about the CMOS, we have to keep in our mind that there is a latch up problem there in the CMOS, unless otherwise if we are not doing proper design. Okay, what is the latch up now? So latch up is actually, there exists a short circuit form between the power supplies. That's what we see. Short circuit current. So therefore, the short circuit current is formed between the power supplies. This huge short circuit current can damage the IC. Whatever the IC that we are making by using the CMOS approach, the huge amount of the current will flow here. The current is very huge amount of the current. If you are not properly manufactured or the designing of the CMOS devices. Okay, so what exactly the CMOS? So how do we apply this latch-up problem in CMOS circuits? Okay, as we can see that there exist a parasitic devices in a CMOS device, CMOS structure. There exist a parasitic devices, or I can say that the parasitic bipolar junction transistors are developed within the MOS structure. Whenever we fabricate the whenever we fabricate the CMOS devices, the parasitic bipolar junction transistor will be formed. Okay, so these parasitics, once it is on, there is a huge amount of the current will flow within the CMOS device from power supply high to low power supply. So there is a huge amount of the current will flow from high supply to the low supply. Okay. So therefore, that leads to excessive current. That current will damage the IC or the device. So let us see, for in the case of CMOS inverter, let us see how the parasitics will be developed. If the parasitics are on, how much amount of the current will flow, and if the current is maximum, what will happen to that one? And if you want to reduce that problem, what are the different remedies are there? So these are the things that we want to notice. Okay. So let us consider how the latchup is formed in a CMOS device, as everybody knows that. For example, this is a P substrate, let us consider. Okay, this is the N substrate. Okay, normally, as everybody knows that is it is a P substrate, right? P well, okay, P well, for example. P well in the sense, what are the transistor that we can form here? We can form here is a N plus, here also form N plus. Here is P plus substrate. So what is here in this case now? What it is in this case? N substrate means P plus source, P plus drain, and this is a P plus, sorry, this is N plus, right? This is N plus, right? Now, how the parasites will be developed there? Okay, as we can see that this P well can act as a, this P well can act as a base of the transistor, base of the NMOS transistor. Okay. So this N plus will act as, this N plus will act as emitter of the NMOS, NPN, emitter of the bipolar junction transistor. This N substrate, this N substrate will act as, the substrate will act as a conductor. Okay, so this is act as a collector. So because this structure shows this kind of parasitic device developed within the CMOS device, and of course, there is a resistance is formed for the P well also. So therefore, the the, another device is formed here is a resistor. Another one is resistor is formed. So therefore, this resistor is connected to this one, to the low power supply, and this is connected to this point. Okay. So these two things are connected to the, right. So therefore, the what kind of transistor that is formed here? It is a N transistor is formed within the well to this particular N substrate, right? So similarly, you can observe here is that. So here there is a possibility of P and N. This is P. So therefore, this is a P transistor. So here towards the ground side, what device will form? There is a PNP transistor. There is a PNP transistor will form. How it will form? Something like this. So there is a base here. What is the base here now? Sorry, I think better I need to take another color. Red color I will consider. So therefore, this is the base. The collector is something like this. Sorry, emitter of the source of the PMOS transistor is act as a emitter of this transistor. Okay, and oh, and this will be collector of the device. This will be collector of the device. Okay, so therefore this is what we observed. This kind of device is observed here. This kind of device is observed here. So therefore, what I can say that, so this is the emitter, right? So this emitter is connected, sorry, this collector. This collector is connected to this collector of this base. Of course, both are p-type only. Okay. So this substrate and this substrate both are equal. This, sorry, this base and the collector both are equal. Both are at the same point. Okay. So this is connected. This is connected to the emitter of the emitter terminal. Okay. Now the N substrate also produces some kind of resistance. Okay. So that resistance is also observed here, and this is connected to. So these are the different parasitics that are developed within the device. Okay. So what are the different transistors that is formed here? Here it is a PNP transistor. So therefore one PNP transistor is there. It is the series resistance. This is called parallel resistance is formed. Two bipolar junction transistors and two resistors are formed within this structure. Okay, so let us take the circuitry. What will happen? Let us see more detailed discussion here. Okay, I think better I draw here itself. Okay, so let us consider the circuit here. Okay, so let us consider the circuit. Consider the circuit. Um, so we have a transistor here, PNP transistor. It is connected to VDD, right? The source is connected to, sorry, base is connected to, through the resistor, it is connected to VDD. This is called RS. Okay. Now we have another transistor here. Sorry. So here we consider that there is an emitter, base. This base and this one must be connected. So that's what here we observed. And this is connected to the resistor here. And this is connected to the lowest power supply. And this one and this one both are at the same potential. So this is what the circuit that is observed in this particular circuit, in this particular CMOS device, right? So you can carefully observe how I have connected and you can get it there. This is what the circuit I'm saying that. So how the maximum current will flow from VDD to the ground? Let us look at now. Okay. So these devices will be active, will come into the picture when there is a glitch on the power supply or incident radiation. So these are the disturbances that we normally face in an ICs. Okay, whenever these things are happen, these devices will come into the picture. Normally, these won't come into the picture. They're inherently available, but it won't come into the picture. But when these things are coming to the picture, these kind of disturbances are arises. Okay, in that situation, what will happen? Any one of the transistor collector current will increases. Either this one may be increases or maybe this collector current may be increases. For example, assume that here the collector current is increases, IC1 is increased. IC1 is increased. So what will happen? Some current will flow here, some current will flow here, right? IC1 is flowing in these two areas by using the Kirchhoff laws. So that means the drop is across here. So this drop will make this transistor becomes on. This transistor, if suppose this drop is very, very high, which is more than that of the threshold voltage of this device or VP of this device, this transistor becomes on, right? So therefore, there is a current flow in this particular current, this here also, IC2 will form. What is the IC2 of this one? As we know that IC2 of this device is nothing but beta 2 times of IP2. What is the current flowing here? The base current. So this is the base current. This base current is multiplied with the beta of this transistor will result IC2. Right? So that means that if this current is from coming means, So this value will come here. This is what actually the current flow will be done. So from here, it will go here and it will go here also. Right? So what is the amount of the current flowing here actually? What is the amount of the, what did I say? So that means the second time, this IC current will influence IC1. This IC2 will influence the IC1 because the current flowing here will be the base current. That base current will also, of course, as we know that the drop across the IS also will activate this device. Okay, so therefore this device becomes on, therefore the maximum, some amount of the current will flow. So therefore this process will be repeated. This process feedback current flow is repeated. That means the collector current of the transistors will be multiplied each other every time. So therefore, so one time some values, another time multiplied the previous, the third time multiplied the second time. So like this, it is a multiplication of the current will flow, multiplied current will flow. So that will generate a lot of heat within the mass structure, within the CMOS devices. Therefore, ultimately, the CMOS device will burn. Right? So that is what actually observed in this particular scenario. Okay, so therefore, when this particular situation is observed, means when beta 1 and beta 2 of the gains of the both transistors are greater than 1, then both the transistor will conduct, which leads to the high saturation current. And even if you're not applying, so first time only the some disturbances that we have applied. After disturbances are applied, even if you're not applying any disturbances, because of that huge amount of the current will flow, it automatically activate the devices. Initially, what happened? The disturbances make the transistor becomes on. Later, once the current max, so once the finite amount of the current is flowing from middle to ground, that itself making the transistor again on and on, again and on and on. So that makes the problem in the circuitry. Okay, so what is the total current in one loop is nothing but current perturbations into gain. So therefore, this is repeated all the time. Okay, so the perturbations, sometimes perturbations are not required after some time. Therefore, whatever the current that is available within the mass structure, that will activate the parasitic transistors. So therefore, how much latch-up current will flow. So whatever the huge amount of the current I told you, that is called latch-up current. This current characteristics something like this. It is gradually increases and reaches to the negative, the transition from high to low resistance, and it reaches to the maximum value. So now it will be reaches to the maximum value. So therefore, the current characteristics are something like this for the CMOS device. Okay, so we have to reduce this problem. So therefore, in spite of power consumed by the CMOS device are less, but this is a problem. We need to solve this problem. How do we solve this problem? So very importantly, one important thing is that we have to reduce the resistance values of this one. If you reduce the resistance value of this one, drop across this VB, the drop across this one is reduces. That drop may not be sufficient to activate this transistor. Okay, so the doping concentration of the wells as well as the substrate, well and substrate must be maintained thoroughly. If you're not maintained properly the resistance values of these things, that means the doping profile, if you're not maintaining properly, uh, the drop across that one makes the transistor become strong. That is one of the important things. That is the reason why the doping concentration of the substrate or a well, we have to maintain carefully. Otherwise, if any current will flow within this particular device, will affect the circuit, right? So that is the obvious solution. Another solution is that just we have to provide the guard rings here, guard rings. So therefore, from well to this one, if you move this one and this one away from this one, so there is no formation of the PMOS transistor here. PMOS transistor form అయ్యే అవకాశం ఉండదు మనకి. So when this well and the substrates are very far from each other, there is no possibility of the current flowing in this one. But it's not a obvious solution. Just we have to use the guard rings here. So the guard rings, by applying the guard rings, no need to move the NMOS and PMOS very far to each other. We can play near to each other, but in between these two guard rings are available. So the guard rings will disconnect this circuit. So disconnect this circuit, right? So this is what the knob-based solution for this one. So these are the remedies that we have to follow, right? So this is what actually we need to concentrate on. Just another topic is already we have seen the past transistors related thing. Okay, so we have to do another one. So mass transistor model. Okay, the time is up. Okay, so just only one mass transistor model I will show you, and then I will drop here. I will stop here. So nothing else in it. Just because of structure, because of its structure, some other devices are also formed within the mass structure. Let us write here is mass structure. Mass circuit model. So what is this mass circuit model says that? Then you can copy here. So this is a mass circuit model. So normally what we observe, so these are the some parasitic also developed within the mass structure. Again, for example, a simple mass device that we consider. For example, here we consider substrate, source and gate, right? Whenever we are diffusing something inside of the substrate, okay, whenever you are diffusing, whenever you're diffusing something here, what will happen? There is a recombination is existed between the this and this. Okay, two diffusions must be recombination will takes place, right? This is n plus, of course. So for example, this is n plus, this is also n plus. This is a p substrate. Okay, what it resembles that? It is simply a diode, right? It is simply a diode. So the diode it formed. So in order to characterize this particular mass transistor in a circuit, in order to model this particular transistor, these things will take into consideration. Of course, these are the two conducting plates. There is a possibility of capacitor here also. Okay, so here also there is a capacitor. There is a possibility of diode. Here also there is a capacitance. Of course, we know that there is a capacitance will form here between the channel to this region. Okay, so like this, different type of capacitances, different type of diodes, all these things will formed within the circuit itself. Okay, whenever we want to use this one in our circuitry for the simulation purpose, so we have to write the mathematical equations based on these parasitic as well, these devices as well. Okay, so now it is possible to simulate the circuit, its behavior. Unless otherwise, if you're not taking into consideration of these particular elements, it is not possible to simulate correctly. Okay, so the circuit, the MOS circuit model means what are the different devices that are developed within the MOS structure. Okay, so that is all about circuit model. So whenever we are simulating this this transistor in your spice code or some other places, and these particular parameters will take into consideration. Okay, so with this, we have come to the end of the unit number 2, and almost all the things we have covered. And please go through it once, the unit number 2. So the assignment for the unit number 3 will be displayed in the modules. Please check once. Thank you. So please go through the lectures once or twice. Therefore, you can understand the concepts. So you can leave, students. You can leave.